Hello, I'm Kfir Sulimany from the Hebrew University of Jerusalem, and I'm a PhD student in Yaron Bromberg's lab for complex photonics. Today I'm going to talk about fast and simple high-dimensional quantum key distribution. In this work, we analyze and demonstrate a novel scheme for fiber-based high-dimensional quantum key distribution, and we show a significant improvement in the secure key rates of the system. Quantum key distribution is a cryptographic key establishing protocol between two parties. Quantum key distribution utilizes superposition or entanglement to achieve ultimate security. The security is ultimate in the sense that we do not assume any assumption on the eavesdropper. That means that Eve can do anything allowed by the physics, including quantum computation. The performance of quantum key distribution is quantified by the achievable secure key rate, which means the size of the secure key transmitted in a second. Let's take a look on the specific structure of a quantum key distribution system. Here we have two parties, Alice and Bob. And Alice and Bob want to share cryptographic key. To this aim, Alice encode and transmit a quantum state on a quantum channel, and Bob can measure those states. In addition, they have a classical channel, which is assumed to be public. This means that everyone can read information in the classical channel. We also assume an eavesdropper that trying to learn the secure key, and he of course can read information in the classical channel, and he can also read and modify the information in the quantum channel. In the quantum key distribution security proof, we show that Eve cannot learn any information about the secure key without introducing detectable errors on the quantum channel. Now I'm going to briefly describe the basic protocol. True single photon sources are not essential for quantum key distribution. And it turns out that the simplest way to implement quantum key distribution is by using weak laser pulses. Here we use a CW laser followed by an intensity modulator that can either block or transmit the beam in order to produce optical pulses. In addition, we use an optical attenuator to guarantee that we have less than 1 photon energy in each pulse in average. The logical bit is encoded in two pulse sequence consisting of an occupied and an empty pulse. Let's take a look on a specific sequence. Here, the first pulse is occupied and the second is empty, and this is a logical one. And here there is an empty pulse followed by an occupied pulse, and we call this combination 0. Bob recovers the bit value by measuring the arrival time of the pulse with a single photon detector. Here is the single photon detector, and to detect attacks, a small fraction of the pulses split to a monitoring line by a beam splitter. Bob checks for phase coherence by using an imbalance interferometer and another single photon detector. Here is the imbalance Michelson interferometer, and it built to interfere two successive pulses. Since all of the pulses were generated in the same CW laser, we know that the pulses should have similar phase relation, and therefore we built the Michelson interferometer to interfere destructively the pulses on the single photon detector channel. Now I'm going to present the concept of high-dimensional quantum key distribution. The information can be encoded in high dimensions. For example, in the previous protocol, we encode information in two successive pulses, and we encode quantum states in a two-dimensional Hilbert space. Instead, we could use 4 successive pulses and encode states belonging to a 4-dimensional quantum Hilbert space. And for example, to use the first pulse to represent 0, the second pulse to represent 1, and etc. This concept is first introduced by these two seminal works. High-dimensional protocols are interesting for higher secure key rates and also greater resilience to noise. If we look on the secure key rates versus the bit error rate for different dimensional encoding sizes, we'll see that in zero bit error rate, we will get 1 bit of information in the case of 2-dimensional encoding, and 2 or 3 bit of information in the case of 4 and 8, and this is just the capacity improvement that we could get in the classical communication case. Now in the quantum communication, there is something more interesting. we can see that each curve has cutoff in a particular bit error rate. For example, in the case of 2, we have the cutoff in about 11%. This means that we cannot encode, we cannot implement quantum key distribution beyond this value. And if we want to implement quantum key distribution beyond this value, we must use higher dimensions. A record-breaking key rate of 26 megabit per second achieved with 4-dimensional protocol and published in Science Advances in 2017. The problem is that high-dimensional quantum key distribution protocols require significantly higher experimental resources in terms of detectors and interferometers. And therefore, implementations of high-dimensional quantum key distribution protocol in commercial system is still held back. Now let's try to understand why do we need so many detectors and interferometers. In the previous protocol, in the binary protocol, we had to interfere 2 successive pulses, and in, for example, 4-dimensional protocol, we should interfere not only 2 successive pulses, but also 2 pulses in a delay of 1 pulse and 2 pulses in a delay of 2 pulses, and therefore we need 3 interferometers, just as they implement in 2017, and of course they should have more detectors. This assumption was thought to be true for many years, and now we are going to present for the first time in a high-dimensional protocol relying only on interfering 2 successive pulses. Since we interfere only 2 successive pulses, we can present a high-dimensional protocol which requires only standard binary hardware. We encode states as a single occupied pulse in a sequence of d pulses, and we group n sequences to a block and apply random permutation sigma to create the permuted key block. Here is the raw key, which consists of n sequences of d pulses, and each sequence consists only 1 occupied pulses and the other are empty. In this example, d equals 3. Then we implement the permutation and we get a permuted key. We then convert the block to a sequence of occupied and unoccupied pulses. For example, this sequence converts to physical pulses in which the second pulse is occupied and the other are empty. We obtain the security based on the same coherence measurement as in the binary protocol. Now, the key point is that in this protocol, since we did this permutation, any two successive pulses could be originated anywhere in the raw key. For example, this yellow and purple pulses are originated very far in the raw key, and it mimics the interference of any delay instead of actually measuring the different options. The security proof of this protocol is published on arXiv and is beyond the scope of this talk. But here I'm going to present the tools we use. The amount of information Alice and Bob share can be quantified by the mutual information. We present Eve's strategy and her density operator for each encoded state. We then compute the Holevo information, and finally we compute the amount of the secure bit per photon, which is the mutual information minus the Holevo information. The number of the secure bit per photon for experimental system and for theoretical model are presented here in this graph. And we can see that the secure bit per photon increases when the occupation is low. This is because that Eve cannot act efficiently in low occupations. And when the occupation is high enough, she can extract all of the information from the link, and therefore we are left with no secure bit per photon. In addition, we can see that when we use higher dimensional encoding size, we can get more secure bit per photon. Now, we are interested in the secure bit per second rather than secure bit per photon. And we know that when we use lower occupation, we will get less photon per second at both sites. We define the secure bit per second as the secure bit per photon times the detected photons per second. Now, the detected photons per second doesn't increase linearly with occupation since the detector saturates at 100 kilophoton per second. Now we will look on the secure bit per second versus the occupation. There are 8 graphs. The solid are for the experimental setup and the dashed are for the theoretical model. And each graph gets optimum in a certain occupation. Now here's the improvement. In 8-dimensional encoding, we get twofold enhancement relative to the standard binary 2-dimensional protocol. And the same is true for the theoretical model. In the paper, we show that we can get this twofold enhancement also for superconducting nanowire single photon detectors and not only for our APD. Last, I would like to present our experimental system used to implement both the binary protocol and also the high-dimensional protocol. The system consists of 2 boxes, Alice and Bob, that are connected by 40-kilometer fiber link. All of the components used to implement this system are commercially available, except for the Michelson interferometer, which is located under the FPGA at Bob's site. The interferometer is built of a fiber beam splitter and 2 fiber Faraday rotator. To conclude, we presented a high-dimensional quantum key distribution protocol, which requires only standard binary quantum key distribution hardware. We analyze the security of the protocol, and we experimentally demonstrate our protocol with a standard binary encoding system. We demonstrate more than a 2-fold enhancement of the secure key rate. Therefore, we think that our experiment paves the way toward a wider use of high-dimensional encoding in quantum communication. Thank you for listening. I would be happy to receive questions.